Okay, so if you have any questions about the gradings in your homework, you should talk with the assistant first, and if necessary, then you can come to me. And about the second homework, you see, the idea of the homework is so that you will learn. The idea is not to make you suffer or to give you low grades, etc. So if you have any questions about the homeworks, you can ask it in recitation hours. Wednesdays are for our recitations. I mean, you can even ask for the homework that is due for this Friday. We can discuss on how you should be solving it. I will not be solving it in detail, but I can give you the steps or the hints. Of course, to be able to ask questions, you should first try on your own to do the homework, and so you will know where you are stuck. Then you can ask me, and we can discuss, and you can just solve the homework until Friday. Now, before we continue, any questions about the things that we had been doing until now? Now, if you remember last week, we were discussing the Laplace's equation. What does the Laplace's equation tell us? And we were discussing also the uniqueness of the Laplace's equation. And the uniqueness, although we will not be stating it explicitly most of the time, what we will be doing in the next couple of weeks will be strongly based on the uniqueness theorem. I mean, they will not have any meaning without the uniqueness theorem. One important property of the solutions of the Laplace's equation, which was this one, is that they don't have any local minima or local maxima. So if, for example, phi is equal to 0 on the boundary of some volume V, and if phi is a solution of the Laplace's equation, then we know that phi is equal to 0 everywhere in our volume. So it has to be, this was the main thing that we used in proving that the solution of the Laplace equation was unique given the boundary conditions. So the uniqueness theorem that we proved was we are looking for a function who is a solution of this equation, the Poisson's equation, with boundary conditions, let's say phi bc on the boundary. So we are given the boundary conditions, and we are required to find the solution of the Poisson equation, not the Laplace equation, but the Poisson equation subject to that boundary condition. And then we said that if we assume that there are two of them, just warn me about those units. I'm teaching 2 electromagnetics courses with use. In both of them, I'm using different units. In the other one, it should be 4 pi. In this one, it should be 1 over epsilon 0. Anyway, so if we have the two solutions, and then we defined phi 3, which was the difference of them. This phi 3 satisfies the Laplace's equation because Laplacian acting on phi 1 gave us minus 1 over epsilon 0 rho. Phi 2, if we act Laplace operator on phi 2, we got the same thing. If we subtract them to get the Laplacian of phi 3, it just gives us 0. And on the boundary, phi 3 is equal to 0. Well, why? Because we know that on the boundary, both phi 1 and phi 2, they are equal to what we call the phi bc. So their difference on the boundary is 0. So basically, that's all we need. Since we have a function that satisfies the Laplace equation, it is 0 on the boundary, so it has to be 0 everywhere. Since it is 0 everywhere, everywhere meaning everywhere inside our boundary. So this means phi 1 is equal to phi 2, everywhere. Again, it will be crucial that this everywhere means inside the boundary. They might be different outside our boundary, but inside the boundary, we know that they are equal. Today we will see a case where we have these phi1, this function which are equal inside our boundary, but they are different outside. Now this was one of the uniqueness theorem which proves that if we know the boundary conditions, then the solution is unique. But it might happen that we might not know the boundary conditions. What we might know is, this is the second uniqueness theorem. What we have now is, let's say we have a bunch of conductors. We know their charges. Let's call this one Qi. And you can have arbitrary number of charges. Now the question is the solution to this problem unique? We don't know how the charges are distributed in the conductor. Since we don't know how they are distributed, we don't know what the potentials of the conductors are. But we know that the surfaces of these conductors are equipotential surfaces. That is the thing we know. Now again, our trick will be basically the same. So we will assume two solutions and try to prove that those two solutions have to be the same. Let phi1 and phi2 be two solutions. So what we will be trying to prove it, again, this phi1, it has to be equal to phi2. And just as in the previous case, we will define phi3 to be the difference. So this phi3 satisfies the Laplace's equation. Well, in fact, both phi1 and phi2, they all satisfy the Laplace's equation in this region between the conductors. Not everywhere, but in the region between the conductors, both phi1 and phi2, they also satisfy the Poisson's Laplace equation. Now, we don't know what we are assuming is, maybe, we don't know. Maybe it is possible to distribute the charges in different ways in our conductors, so that each conductor might be a different equipotential. One example, one question, let's say. Suppose we have this positive charge here, this negative charge over here. They are very close to each other. And now we connect them. We take a conductor, take one end to the Andromeda galaxy, and then bring it back, and connect it. Well, this wire goes to the Andromeda galaxy, so I mean, basically these charges, since they are very close to each other, they might be attracting each other, so they will stay there rather than going to the Andromeda galaxy and back. So they might stay in this configuration. This is one possible configuration where we will have some potential created everywhere. Or it is possible that these charges might go to the Andromeda galaxy through this conductor and come back and neutralize everything, so we have zero potential. So that's the kind of thing we want to discuss. Is this possible? Is it possible that we have these two different solutions? So the potentials on the conductors, we don't really know. Phi1 and phi2, they can have different values on the surface of the conductors. We know that the surface is an equipotential surface, but phi1 and phi2 can take different values. So we cannot really use the previous theorem. Remember, in the previous theorem, we knew that at the boundaries, the potentials were equal, so the difference was zero. So that is what we had used in the previous uniqueness theorem. Now in this one, let's consider this expression. We have this phi3 potential, and we have E3. The E3 we define as minus the gradient of phi 3. And let's take the gradient of this one, or the divergence of this one. Now the divergence of this one is divergence of gradient of phi dot E3 of phi 3 scalar product with E3 plus phi 3 times the divergence of E3. Now, in the region, in the volume between the conductors, divergence of E3 is equal to 0. Well, because basically there are no electric charges in those regions between the conductors. All the charges are on the conductors. And gradient of phi 3, we had already said that this is equal to minus E3. So what this tells me is phi 3 times E3, if I take its divergence, this is equal to minus E3 squared. The second term is 0, the first term just gives me minus E3 squared. Now let's integrate this thing over the volume between the conductors. Let's integrate it over the volume between the conductors, and let's call that volume over the volume V between the conductors. Let's name it V. On one hand, we know that integral of divergence of phi 3 times E3 dV over all the volume. Well, we can use the divergence theorem. The divergence of a vector field integrated over a volume gives me a surface integral. This is the integral over the surface of phi 3 times E3. Now, our surface is kind of a weird surface. You see, our volume was all this volume between the conductors. The surface is, well, we have the surface at infinity, plus the surface of this conductor, plus the surface of that conductor, plus the surface of this conductor. So our surface is kind of, we have one surface here, another surface here, another surface here, etc. So they are just disconnected surfaces. So this surface integral is just the sum. Now this is ds. Sum over all the surfaces of surfaces Si, let's call it. The charge Qi has a surface Si the integral is over Si of phi 3 E3 dot ds. Now remember, the surface is an equipotential surface. Conductor surfaces has to be equipotential surfaces. So phi 3, remember, this is equal to phi 1 minus phi 2. Phi 1 is the electric field, one possible electrostatic potential. Phi 2 is, let's say, some other possible electrostatic potential. So both of them are constants on our conductors, on the surface of the conductors. So this difference on the surface of our conductor is a constant. Because phi 1 is a constant, phi 2 is a constant on the surface of the conductor, the difference is a constant. If the difference is a constant, I can just take it out of that integration, because this integral is over the surface of one conductor. And we are summing over all conductors. So since phi 3 is a constant on that surface, I can take it out. This is equal to sum over the surface Si. Remember, Si is the surface of the conductor that carries the charge Qi On this surface, the potential phi3 has the value, let's say phi3I. It can have different values on different conductors. It doesn't have to be the same value of E3 dot ds. Now, phi3 on different conductors can be different. It can have different values. But on each one of on one conductor, its value is constant over the surface. That is what I'm using here. Because this integral is over the one surface, and then over the other surface, and then over the other surface, and I'm summing over all these surfaces. So I took it out. What remains? Let's look at what remains. E3 dot ds. We have a closed surface that we called SI. This is equal to over the closed surface of E1. E1 is the electric field created by the charges, minus E2 is the other possible alternative electric field created by the charges over the surface SI. Now let's remember the Gauss theorem. So what is this integral? What is Q enclosed? Qi, because I'm integrating over the surface of the conductor, which the surface I called it SI. The surface of the conductor that carries the charge Qi. So inside this surface, the total charge is Qi. So this is equal to Qi over epsilon 0. This is the first integral. But the second integral is also an electric field, so it is also Qi over epsilon 0. And hence this integral is 0. So each one of these integrals is itself 0. So the sum is 0. So that basically proves that the integral over all of my volume, which is the volume enclosed by in between the conductors, of divergence of phi3 E3 dV, this is equal to 0. So what we did is we just converted into surface integral. Our surface is just disconnected pieces. So we wrote that surface integral as the sum over the integrals over each one of these disconnected pieces. But the integral over each one of these disconnected pieces was 0, so the sum is 0, and hence this volume integral is 0. Well, you see, what I did was, we are searching for this possibility. Okay, in this conductor, I put a charge Q1. In the other conductor, I put a charge Q2. In this conductor, I put a charge Q3. In the other conductor, I put a charge Q4. Okay? So, and then I just let them go. So the question is, they will distribute themselves. But is it possible that they distribute themselves according to the way that we prepared the system? For example, this was the example I was mentioning. Let us assume that I put a plus Q charge at this end and the minus Q charge on this end. So maybe they will just stay there because they will be attracting each other. Or I can just don't put any charge anywhere. It's a neutral system as a whole. So this is a different way that I prepared the same system. So there are two different ways I prepared my system. Is it possible to create two different electric fields everywhere? That is what I'm looking for. And what we will be proving that it's not possible. So given the total charges of the conductors, the charges themselves distribute them in a unique way, kind of independent of how we put the charges there. That is what we will be proving. To prove that, what I did was, let's assume that it is possible that depending on how we put the charges initially, we can end up having different charge configurations. Although the total charges are the same in each conductor, we might some of the charges might be stuck at certain regions, if we put some charge over there, or some other charge might be stuck some other place, depending on how we put the charges. We put the charges in one way, and we create the potential phi1 and the electric field E1. We put the charges in some other way. We created the final configuration in a different procedure, let's say. The final configuration is the same in the sense that the total charge of each one of the conductors is the same eventually. But we just come to that final configuration in a different way so that the charge distribution in the conductors will be different. And so they will create this potential phi2 and electric field E2. Is this possible that phi1 and phi2 are different? Is it possible to create different charge configurations in our metal by preparing our system in different ways? And we will prove that it's not possible.
O zaman hocam elektrik alanda mı local maksimum ya da minimum sabit?
You see, maximum and minimum is a property of numbers. You can compare two numbers. You can say that a number is larger than or smaller than. You cannot say a vector is larger or smaller than another vector. Now, there is one step left, and then our proof will be done. So on one hand, this integral is 0. On the other hand, we had shown that this divergence is actually minus E3 squared. In our volume V. But you see, E3 squared is always positive. Minus E3 squared is always negative, or 0. If you just sum 0 or negative numbers and you obtain 0, it just means that all those numbers are 0. E3 cannot be non-zero. If E3 is non-zero at a region, that means this integral will be negative and it cannot be 0. But we know that this integral is 0. That basically tells me that E3 squared is equal to 0 everywhere. And hence, E1 is equal to E2. So you cannot create different electric, if you know the total charges in the conductors, you cannot create different electric fields by preparing your system in different ways. For example, here, let's go back to this example. What is the total charge of this conductor? 0. So 0 electric field is a solution of our Poisson's equation with this total, consistent with this total charge. So that is the only possibility. There is no other alternative. The positive and negative charges cannot stay in this configuration. They will neutralize. You see, when you are talking about infinities, you have to be a bit careful. They are not physical. In real life, you don't have infinites. Nothing is at infinite distance. Well, if Andromeda galaxy, for all practical purposes, is infinite enough. And if you take this wire to the Andromeda galaxy, or one of them to the Andromeda galaxy, etc., they will neutralize. There is a catch, though. Just keep in mind, we are talking about electrostatics. If you take, I don't know, if you make this wire very, very long to the Andromeda galaxy, or I don't know which is your favorite galaxy and back, well, it might take years for the system to reach electrostatic equilibrium, statics. But when it reaches the static case where you can apply electrostatics, They will be neutralized, no electric field anywhere.
Yani hocam şimdi biz böyle farklı kondaktörleri koyduğumuz zaman bunlar birbirlerini nötrlemeye mi çalışıyor?
Not necessarily. I mean, you can put positive charges there. What we are saying is, if you have many conductors nearby, you put some charges on them. Then there is a single possible configuration So the electric field is uniquely determined by the total charges. We don't know what it is yet, but it is unique. There's no, well, if the charges do this, then we have such an electric field, or if the charges do the other way around, there's another electric field. No, there are no alternatives. If you believe that there are two different solutions, then there is something wrong that you are doing. You are missing something. The solution is always unique. If you know the boundary conditions, or if the charges are on the conductors, and you know the total charges, then the solutions are unique.
Hocam biz bu volüm üstünde konuşuyoruz değil mi? Hani şuradaki volüm hakkında bir şey demiyoruz.
Well, one of the boundary of the volume is at infinite, at infinity. Or you can put a conductor around and talk about that boundary. I mean, it can be nearby. Now, then the question is, okay, fine, we prove the uniqueness theorem, etc., but how can one come up with the idea of considering this expression to prove the uniqueness? I have no idea. We know that it works. It tells us what we want to say, what we want to know, but well, that's, I would say, let's say, the sign of a genius, that somebody thought that maybe we should consider this expression and do the steps, and you have the uniqueness theorem. So I don't have a logical reason of how one can consider this expression. Now let's do an application of these. An application is the method of images. Now, if you had a hard time following the uniqueness theorems, their proofs, don't worry. What we need to know is that given the boundary condition, whether it can be, okay, we have these conductors with total charge such and such, or the potential should have this value on the boundary, etc. Given the boundary conditions, the electrostatic potential is unique. If you somehow come up with a solution in your volume, by whichever trick you have in your casket, if you come up with a solution, that is the only solution. There's no other alternative solution. So that is kind of the nice thing about the uniqueness theorem. It just lets us to whichever clever trick you know, just use them. If you can come up with a solution that satisfies the Laplace's or Poisson's equation and also satisfies your boundary condition, the solution is unique. Now let's look at this one. An infinite conducting plate which is grounded, and we put some plus Q charge over here. Now what is the potential everywhere? Now first let's look at what is the potential on this side. On the left-hand side. Does it satisfy the Laplace equation or the Poisson equation on the left-hand side? Why? Well, there are no charges on the left-hand side, So remember, the potential always satisfies this equation. So if there are no charges, the charge density is 0, so rho is 0. So it satisfies the Laplace equation. Now what is the value, what is my boundary on the left-hand side? Well, my boundary of, this is my left-hand side. I'm looking at the potential here. One boundary is this one. And if I cross it, I'm on the right-hand side. I'm looking at the left-hand side only. So this is one boundary. What is the value of my potential on this boundary? 0. Well, this boundary only doesn't cover my volume. I have to specify the value of my potential on the boundary of my volume everywhere. So my volume, the surface of my volume, one side is this one, the other one is at infinity. And what is the value of my potential at infinity? 0. The charges are localized over here. This is my plus charge. My charge is only over here. So at infinity, they will not have any effect. So at infinity, my potential is also 0. By the way, most of the time when we say grounded, we just mean that the potential of this conductor is set equal to the potential at infinity. So if we choose the potential at infinity to 0, then the plate is at 0 potential. At infinity, my potential is again 0. And phi is equal to 0 on the boundary. So what is phi everywhere in my volume? What is a function that satisfies the Laplace equation and is 0 on the boundary? The easiest one, the simplest one, 0. We guessed it. Well, does it satisfy our equation? Phi is equal to 0 everywhere. Does it satisfy the Laplace equation? Does it satisfy the boundary condition? So the solution is unique. So this is a solution of these equations. So it is the only solution. There are no alternative solutions. So on the left-hand side, the potential is 0. There is no potential. The potential is constant, so there is no electric field. On the left-hand side, the electric field is 0. Now let's look at the right-hand side. What is the potential and the electric field on the right-hand side? Now, we know the boundary condition. Well, there are two things that we have to pay attention to. It should satisfy this equation, potential on the right-hand side. Well, there is one charge on the right-hand side. There's a point charge. Let's say its position is R0. There's a charge at the point R0. Or let's call it R plus. No, R0, sorry. Is minus 4 pi, the three-dimensional Dirac delta of R minus R0. Q over epsilon 0 times Dirac delta R minus R0. And phi is equal to 0 on the boundary. Well, again, if you look at the right-hand side, my boundary is one part of my boundary is again this plate, which is at 0 potential. The other side is at infinity, which is again at 0 potential. Well, you see, this time the solution is not 0, because phi does not satisfy the Laplace equation. It satisfies the Poisson equation. And so it can have a local maximum. In fact, except at the point R is equal to R0, it does satisfy the Laplace equation. But at the point R is equal to R0, we will see that the potential is infinite. So it has an infinite value at the R0, and then it goes to 0. If you just plot it, it just looks like a tent. just a peak, and then it goes to 0. Let me look at this function, the potential created by this distribution. Let's say this is at R0, the charge plus Q. It is at a distance d from my plate. Let me imagine I put another charge, minus Q, at the point R0 prime. This is a different problem. In the real problem that I'm looking at, there is a conducting plate over here. I have a single charge, and now I just change my problem slightly. I have two charges. I'm just creating a dipole. And the potential created, let's say, at this point, at the point R, would be plus Q over 4 pi epsilon 0, 1 over R minus R0, plus minus Q over 4 pi epsilon 0, 1 over R minus R0 prime. It's just two charges. I add their potentials. Now, what is the value of this potential along this middle line, middle plane? This is also D. Well, on the middle plane, if R is on the middle plane, well, the middle plane is equidistant from both of the charges. So that just means that the distance of R from R0 is equal to its distance from R0 prime. But if these distances are the same, well, I have a plus Q over 4 pi epsilon 0, minus Q over 4 pi epsilon 0, so the result is 0. Phi of R is equal to 0 on the middle plane. Now, when I act with Laplacian on phi, what do I get? No. Well, I know that this is the potential created by a point charge at the point R0. And so the charge density corresponding to this point charge will be Q over epsilon Q times the Dirac delta of R minus R0. Then I have the Laplacian of this expression, which is again another point charge located at the point R0 prime. So the corresponding charge density will be minus Q over epsilon 0 Dirac delta of R minus R0 prime. Still not the solve. I mean, this phi doesn't satisfy the equation that I was looking for. Remember, I am trying to solve this equation with this boundary condition. Now, I wrote this phi, but this satisfies this equation. This is nice. This is what I wanted. This is not what I wanted. But just pay attention to one thing. On the right-hand side, R is never equal to R0 prime. So on the right-hand side of this middle plane, this is always 0. This is non-zero only when R is equal to R0 prime, but that is not on the right-hand side, that's on the left-hand side. So on the right-hand side, Laplacian of phi is equal to minus Q over epsilon 0, Dirac delta of 3R minus R0. So now I have these two systems. One is this one. The other one is this one. And this is the middle line. Now, in this system, if you look at what we are looking for a function that satisfies the Poisson equation with a single Dirac delta in this volume with boundary conditions that it is zero everywhere. I know the solution of this one, which satisfies the same Poisson's equation in this volume, and on the boundary of this volume, it satisfies zero boundary conditions. Are you following? Now, we wrote down the solution of this equation, okay? This system. We wrote down the potential. Nice. The top line. We have the potential corresponding to this system with plus Q charge and the minus Q charge. What do we know about that potential expression? It satisfies this equation on this plate, on this half space. Furthermore, on this line it is infinite. On this plate it is zero. At infinity it is zero, that function. But here, what were we looking for? We were looking for a function that satisfies this equation in this plate, in this half space, satisfying zero boundary conditions. There we have one. So it is the solution. So now we can write the potential. Phi of r is equal to q over 4 pi epsilon 0 times 0 if r is on the left-hand side, and 1 over r minus r0 minus 1 over r minus r0 prime if r is on the right-hand side. So this function satisfies my Poisson's equation and my boundary conditions. So it is the solution.
Left-hand side
No. You see, we first divided our space into two different regions. So this we didn't have to do anything. This conducting plate divided our space into two regions, the left-hand side and the right-hand side. And we are looking for the solutions on the left-hand side and also on the right-hand side separately. On the left-hand side, the potential satisfies the Laplace's equation, and it is zero on the boundary. So it has to be zero everywhere. So that is the solution for the left-hand side. What remains is to find the solution on the right-hand side. And on the right-hand side, we said that, okay, instead of this problem, let's look at the problem in which we have this charge, and there is a corresponding image charge on the other side. Of course, there is no such charge, but it's just an image. And we had seen that this system, the potential of these two charges, satisfies all the properties that we are looking for on the right-hand side. We are looking for a solution on the right-hand side, and the potential of these two charges has all the properties that we are looking for on the right-hand side. It satisfies our Poisson equation on the right-hand side, and it is also zero on the boundary. Yes. We are saying that this system and the dipole system, these two systems are identical on the right-hand side. Not on the left-hand side, but on the right-hand side they are identical. What do you mean? Okay. Well, I mean, it doesn't exist. I mean, if you want to look at the dipole system, which is not our system, yeah, you can say that one is a positive height, the other one is a negative sink, if you like. But that charge doesn't exist. This is our system. So what is happening here is we put this positive charge over here, and we are grounding it. It kind of attracts negative charges on the plate. Well, the closer points will have a larger negative charge. As you go further away, there will be less negative charges. So this is the actual charge configuration of our system. But this charge on this plate, on this conductor, on the surface of this conductor, they just behave as if there is a negative charge on the other side. In this sense, it is called the method of images. So if you look at the mirror, what happens is the light rays are reflected from the mirror. And so you see as if the light rays were coming from the other side. So you think that there is something else on the other side of the mirror, although there is nothing. The same thing over here. These charges on the plates, they behave as if there is some other charge on this other side. So there is an image on the other side.
Hocam böyle image deyince orada da artık Q olması gerekmiyor.
Well, you see, if you look at your image, you are right-handed, right? No, you were left-handed, weren't you? Pick one. Well, he is right-handed. She is right-handed. When she looks at her image is left-handed. So the image is the opposite charge. Well, in your homework, you had already calculated you were given the electric field corresponding to this system, and you calculated the charge density on the surface, and if you calculate the total charge on this plate, it is actually minus Q. I think we did that, right? In the class, we somehow discussed some of the steps.
Bir daha yapalım ya.
Tomorrow. Any questions on this method of images? Yeah, you see, there is no guarantee that just a single charge would have been enough. So we just gave it a try, and it just turned out to be enough. So we just kind of tried a function to see whether it satisfies our equation and also the boundary condition. The function we chose, it worked fine, so great. So we didn't, and the uniqueness theorem tells us that there is no need to search for other solutions because there is no other solution. This is the only one.
Peki şu tarafta da aynı bir plate olsaydı ne olacak? Hani bu yük ikisi arasında dönüyor.
So we have two grounded plates. And we put some charge over here. Well, let's see. First of all, there will be, due to this plate, there will be an image charge. Well, for all practical purposes or for all applications on this side of this plate, it will be as if I have two charges only, two real charges. Well, this plate will see both of these charges. So it will create an image of both of these charges on the other side. So the plus Q will have a minus Q image, and the minus Q will have a plus Q image. But you see now, this plate doesn't see this one only. It also sees this one and this one as real charges. Because on this side of the plate, these two charges just act as if they are real charges. So there will be, this minus q will have an image on this plate, which is somewhere over here, which will be a plus q, etc. You have infinitely many images. Just think of it as yourself being in front of, in between two perfect mirrors. And if you go to some restrooms in some of the the shopping malls, they have mirrors everywhere on both sides, so you can test it. You will see many copies of yourself. Exactly the same phenomena.
O zaman ne oluyor? Sistem tanımsız mı?
No, it's just an infinite sum. In this one, and the single plate. Well, you know the potential, right? We had determined the potential. So once you know the potential, you can calculate the electric field. So you know the electric field on this side of the plate. You know the electric field on the other side of the surface of the plate, which is 0. You can calculate the discontinuity in the electric field. And that discontinuity as you cross this point on the surface is just sigma over epsilon 0 in the normal direction. So just calculating the discontinuity in the electric field, you can calculate the charge distribution. Okay, let's give a 10-minute break, and after the break, we will continue.